Okay, so in this question, we're given a 4-bar linkage. Cool. And then we're told that OA and BC are parallel. So these two are parallel to each other at this point in time. And then points A and points B are connected by the link AB. Okay, then they give us the lengths of the particular links. And we're also given that L is equal to 100 millimeters. We're also given the angular velocity of OA, so of this link over here, and it's going in that direction. And then we're also given the angular acceleration of the same link. And then part A tells us to show that the angular velocity of link AB is 0. So whenever you get two links that are parallel, so like these two in this case, those two are parallel, and if you have a link in the middle connecting the two, the angular velocity of this link here will always be 0. Okay, and we'll prove why that is now. Okay, so what we want to do basically is we want to write the relative velocity equation between point A and point B, right? So basically we need an equation that's going to have omega AB in it, right? An equation that has omega AB in it is the relative velocity equation between point A and point B. Okay, so you can write the relative velocity equation. VA is equal to VB plus VA relative to B. Cool. Then we can break this down and say VB, this breaks down to the relative term will break down into omega AB crossed with R AB, right? Cool. Note that this is only true for 2 points on the same rigid body. If we were looking at two particles in space, for example, so if this was A and this was B, then A relative to B, VA relative to B would not be equal to omega AB crossed with R AB, because these are two separate points, right? These are two separate points. They can't have a angular velocity. Angular velocity is only applied to rigid bodies, right? So in this case, because these two are not connected, they can't have an angular velocity, but they can still have a relative velocity, right? So yeah, in essence, in short, this is only true for 2 points on the same rigid body. And note that VA relative to B, and if the 2 points are not on the same rigid body, it doesn't mean that the relative velocity is automatically 0. Okay, I hope that makes sense. Cool, so we have this angular velocity term, which is what we wanted. Cool, but now we don't know what VA and what VB is, right? So cool, let's try and figure out what they would be, right? So we can draw link OA, right, to try and figure out what the velocity of A would be. Okay, so link OA is going through fixed axis rotation, so it's rotating about point O, and then we can write the relative velocity equation between point A and point O, right? And then VO is going to be 0 because O is a fixed point, so VA is going to be VA relative to O, which is just going to be omega OA crossed with R, right? Cool. Now, this term over here is always perpendicular to R, right? So you're basically taking a vector. Remember, when you take the cross product of two vectors, you get a vector that's perpendicular to both lines. So we're going to get a vector that's perpendicular to R, and R is just this line here, right? And you're going to get a vector that's also perpendicular to this, right? But this vector here is in the K direction, which is pointing out the page, right? So you want to really be able to see that it's perpendicular. You kind of can, because yeah, okay, whatever. But just know that because you're taking the cross product of two thingies, your vector is going to be perpendicular to this one. You don't really need to worry about this one. In essence, it's going to be perpendicular to this vector because this is in the K direction. It's pointing out the page, and your vector lies on the page. Yeah, if you can visualize that, then cool, I hope that helps. But if you can't, don't worry about it too much. Just know that your vector will be perpendicular to R itself, right? And R is this line, the distance of this line OA, and our vector will be something like that, VA, and it's going to be perpendicular to this line. Cool. Then let's do what's it, CP. Okay, so CP, we don't really know if it's rotating this way or if it's rotating the other way. So what we'll do is we'll just draw our vector going something like this. So again, BC is going through fixed axis rotation, right? You have this thing, it's going through fixed axis rotation. Yeah, cool. So if you write the relative velocity equation, Vp is equal to Vc plus V P relative to C, Vc is 0, so Vp is equal to Vp relative to C, which is equal to omega Bc cos with R Bc, okay? And it's going to be perpendicular to that vector there, so it's perpendicular to that, okay? Cool. So we know what the direction of VA is, okay? So we know it's pointing this way. As for VP, we don't really know where it's pointing, but we have the sense of it. I think they call it the sense. So you kind of like know, you know that it's going to be perpendicular to this line, but you don't know if it's going to point that way or if it's going to point that way, right? Cool. And then we can kind of add these two vectors together. So remember, our equation is VA is equal to VP plus VA relative to B, okay? And in vector addition, VA is going to be our resultant vector, so our quote-unquote resultant vector. And then these two vectors, will connect them tip to tail. What? Yeah, so the arrow of one vector, so if that was VP, VA relative to B will start here and it will end at some point. For example, this is not actually how it's going to look, this is just an example. So this would be VA relative to B, and then VA would start at the tail of VP and it would end at the head of VA relative to B. So it would start at the tail of VB and end at the head of VA relative to B. So this is your resultant, basically, which is the sum of the two, and then the ones that you're adding, they're connected and from head to tail, if that makes sense. Okay, so I guess, yeah, I hope that kind of makes sense. When drawing vector diagrams, always start with the vector you know the direction of. It's always a good idea to do that. So we know VA, okay? We know VA, and we know that VB is going to be parallel to VA, okay? Reason why we can say that is these two lines are parallel, and these two lines are also parallel, well, not parallel, they're perpendicular to those parallel lines. So in essence, they have to be parallel to each other as well. Okay, so our VB is either going to act this way or it's going to act that way. And we said VA is our resultant, right? So it's going to start at the tail end of VB, right? And it's going to end at the head of VA relative to B. So VB needs to act in this direction, right? Now, VA relative to B could be a vector that starts here and ends here, right? But there's a rule that the relative velocity vector needs to follow. Okay, if you remember, we can break this up into omega AB crossed with RAB. And as soon as you break it down into this form, the vector that you get from this needs to be perpendicular to RAB. Okay, so let's draw VA and VB, and let's draw in this RAB to get a better idea of how the relative velocity would look, right? So I'm going to draw in point A, point B. We know that VA is going to act this way, okay? We've also discovered that VB is also going to act this way, okay? Now, we said that the relative velocity term has to act perpendicular to this AB. So the relative velocity term is going to be something like that, right? So this is VA relative to B. Could either act this way, could either act that way. We're not sure yet. Okay. Now, if you try and construct a triangle with these three vectors, so we have VA going this way. We have VB, and then if you try, so at the head of VB you're going to have VA relative to B, but we know it's either going to act that way or it's going to act that way. You'll see that we can't draw a triangle no matter what we try and do, right? So in order for VA to be the resultant, right? In order for VA to be the resultant, VB has to be equal to VA, right? I hope that kind of makes sense. So if VB is equal to, if these two are equal, then this has to be 0. And in order for this to be 0, this has to be 0. because this can't be 0, that's a set distance. The distance can't be 0. So your omega AB is 0. So what you would write is, from this vector diagram, you would get that VA is equal to VB, which would imply that VA relative to B is equal to 0, which would imply that omega AB is equal to 0. Cool. I hope that makes sense. Okay. Then this is part A. For part B, we're asked to determine the angular velocity of the link BC. Okay. Which isn't too bad. Okay, so with this question, you start with a link where you know a lot of information. So link AO, we have quite a bit of information. We know the angular velocity, so then we can calculate the velocity of A. Okay, and then we've just proved that the velocity of A is equal to the velocity of B. So if we know the velocity of A, we know the velocity of B. If we know the velocity of B, we can relate that to C to get the angular velocity of BC. Okay, so that's basically the method we're going to try and apply. Okay, so we have omega AO here, and we have A. So we're going to say VA is equal to VO plus VA relative to O. VO is 0, so VA is equal to omega AO cross with R AO, right? Cool. We know that, so we can solve for VA. We've seen that VA is equal to VB. Okay. So VB is also equal to omega AO crossed with R AO. Okay. Then we've also seen, or rather let's analyze link BC. Okay. If we look at link BC, we can say VB is equal to VC plus VB relative to C. VC is 0, so VB is equal to omega BC crossed with RBC. Okay, we know VB, we know that, we're trying to solve for that. So you can basically solve for this question. Okay, I hope that makes sense. And then for part C, calculate the angular acceleration of link AB. Okay, so we're gonna deploy kind of a similar tactic to part B, right? So we're gonna start at the point where we know the most information. So we're gonna start with this link, and then we're gonna find the acceleration of A, and then we're gonna try and find the acceleration of B, and then we're gonna relate the two together to try and find the angular acceleration of AB. Okay, so let's first start with an equation that has the unknown that we want, right? And then let's take it from there. So we have acceleration of A is equal to the acceleration of B plus the acceleration of A relative to B. Then acceleration of A relative to B will have a tangential component, and it will have a normal component. This tangential component will be equal to alpha AB crossed with R AB. and then the normal component will be equal to minus omega AB squared times R AB. Okay, cool. Then we have this unknown, right? So we don't know what this is. And we proved in question 1 that this term over here is 0, right? So this falls away. Then our equation becomes acceleration of A is equal to acceleration of B plus alpha A B crossed with R A B. Okay. Hope that makes sense. And hopefully now you can see why we need to figure out what acceleration of A is and what the acceleration of B is. Once we can find those two accelerations, we can solve for alpha AB. Okay, cool. So let's try and find acceleration of A. So if we look at AO, right, we're given the acceleration, the angular acceleration, AO, and we can write the relative acceleration equation. So acceleration of A is equal to acceleration of O plus acceleration of A relative to O. O is a fixed point, so it's not accelerating. So the acceleration of A is equal to acceleration of A relative to O tangential plus the acceleration of A relative to O normal. Cool. So acceleration of A is equal to the tangential component will condense down to this, and then the normal component will be equal to minus omega AO squared times R AO. Okay, cool. So now we have the acceleration of A. Okay, fine. You'll be able to calculate that. There aren't any unknowns here. We're given that from the question. This you can get, it's just the distance between there and there. It's the position vector between O and A, and this is also the position vector between O and A. So we can find the acceleration of A. And the acceleration of A will be, I'm just going to write it and in components. You'll see why later. So we're going to have A I hat plus A J hat, right? Yeah. But you can just go and calculate it, and you'll get the values for the x component and you get the values for the y component. Cool. So we can then move on to acceleration of point B. So the acceleration of point B requires us to look at link BC. Okay. We aren't able to look at AB. We kind of already did that, and we found that we need another method to get acceleration of B. So we'll look at BC. Okay. Cool. Let's look at link BC. Right. So we don't know what alpha BC is, right? It's not given to us, right? But we know that C is a stationary point, and we've also calculated omega BC from the previous question. So let's write down our full acceleration equation. So C is a stationary point, that's 0. So AB is equal to AB relative to C tangential plus AB relative to C normal. And then the tangential component is equal to alpha BC costed R BC. Don't know why I raised that. Okay, plus minus omega BC squared times R BC. Okay. So alpha BC, right? Alpha BC we don't know. RBC we know. Omega BC we calculated in part B, right? So we calculated it there. So we know that now, we know that as well, right? So now you'll be asking yourself, why or how are we going to be able to solve with these two unknowns? So we have alpha BC, that's unknown, but we also have alpha AB, that's not known, right? And we're trying to solve for alpha AB. If you do the vector method, so you basically find acceleration of B as a vector, which you should be doing, by the way. I keep forgetting to write vectors. Just remember that. Remember to write your vectors. So this is going to break down into your I and your J components, right? So you're going to get something, 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 alpha BC in the I hat direction, plus something, 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 alpha BC in the J hat direction. Okay. Cool. Now if we substitute that back into this equation, we're going to get acceleration of A in the I hat direction plus acceleration of A in the J hat direction will be equal to something, something, something. So we're substituting what AB was over here basically. So times alpha BC in the I hat direction plus something, 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 alpha BC in the J hat direction, right? And then we can also do the same for this, right? So if we simplify it, if we take the cross product and we simplify it, we're going to get something in the I and J direction, right? So we're going to get something, 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 alpha AB, I hat plus something, 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 alpha AB in the J hat direction. Cool. So let's add those terms in. Just going to put brackets so that you know this is what acceleration of B was. And then this is now our acceleration of A relative to B. Okay. So we're going to get something, 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 alpha AB in the I hat, and then something, 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 alpha AB in the J hat direction. Cool. Now we have two unknowns, but secretly we also have two equations. So we need to compare all the I terms, and then we compare all the J terms. So we're going to get acceleration of A and the I hat is equal to blah 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 alpha BC and the I hat plus blah 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 alpha AB and the I hat as well. Then we can compare J terms. So all your J terms, you'll get alpha A J hat is equal to blah 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 alpha BC J hat plus blah 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 alpha AB J hat. That's equation 1. That's equation 2. Then you just solve these two equations simultaneously and you'll get the answer for AB. Okay. I hope that all makes sense. Yeah.